Alright, so here I've got a beautiful parabola. Y equals x squared is the equation of this parabola. And take a look at this point right here, x, where x equals -1, right there, x equals -1. Imagine a tangent to the parabola at that point. Can you picture a line, tangent? Picture it, you might see, oh, there it is. What is the slope of that line? Well, look at the squares and count. Down 2/1, that's a slope of -2. Let's put that into this Excel spreadsheet I created. And let's look now back at our graph, make that go away. What about at x equals 0? Can you picture what the tangent will look like at x equals 0? Maybe you see that. That's what I see. What's the slope of that tangent? You're right, it's 0. Versus 0. What about at x equals 1? Hide this. What is the slope of the tangent at x equals 1? Can you picture it? There's the tangent. Its slope is rise 2/1, run 1, 2/1. The slope is 2. What about at x equals 2? These are just random points I picked on here, but there's 2. X equals 2 on this line. What is the slope right there? Well, let's draw the tangent. The slope is rise up 4/1. The slope is 4. Look at those slopes. They make a nice straight line. These lines can be described, this line can be described by the function y equals 2x. So, suppose I wanted to predict what the slope would be at x equals 3. I can use this function, plug in 3 for x, 2 times 3 is 6. I predict that at x equals 3, the slope would be 6. And I should have made one that confirms that, but you can imagine a line at 3, the slope would be 6. So, for the function y equals x squared, we can use the function y equals 2x, a different function, y equals 2x, to predict the slope of a line at this. This new function, y equals 2x, is called the derivative function of y equals x squared. Take a look at another one. This is the equation y equals x cubed. Let me clean up my spreadsheet here. Delete. Delete. You have to delete also. Delete. Delete. What? Imagine y equals x equals 1. What is the slope to this curve at x equals 1? X equals -1. The slope is 3. Up 3, rise over run, 3/1. The slope is 3. 3. What about at x equals 0? The slope is 0. There's the tangent line at x equals 0. Tangent line, remember, touches the function at exactly 1 point, which this does. So that is the tangent. Its slope is 0. What about at x equals 1? What's the tangent look like at x equals 1? There it is, x equals 1. The slope is 3. And look at those points. They form a parabola. And it's supposed to show the equation for that parabola, but it doesn't seem to be doing it. I think I've reached the capacity of this Macintosh for computing power. Let's look at x equals 2. There's the slope. If I enter into my equation here, 2, I get that. I've completely lost my graph. There it is again. Oh, that is ugly. Shouldn't look like that. Oh, the slope here isn't 2, it's 12. 12. There it is. And this can be described by the function y equals 3x squared. It's got a little weird negative, but look, that's 2 times 10 negative, that's basically 0. That's just a computer error. The actual equation of this parabola is y equals 3x squared. So if I want to predict, if I want to determine the instantaneous rate of change of an object that is moving according to y equals x cubed, I can use this function, y equals 3x squared. I can predict that the tangent will be 2 what the tangent will be at 2 by plugging 2 into this equation. 3 times 2 squared is 12. I can predict that that would be 12. Notice that this cubic function, its derivative function, is 1 degree less, a quadratic. On the previous example, on a second degree function, its derivative function was a linear, 1 degree less. So the derivative of a function is itself a function.